So we've talked about the idea of the disk method, and the disk method has to do with measuring the distance that a function is from the x-axis and then revolving that around to generate some sort of moving cylinder. But the problem is that that really only helps if you have some sort of region that's bounded here and comes up again like that vase shape. So if we don't want to do a vase, so we want to do arbitrary regions, how do we do that? Well, what we can do if we have something like this where these things are bounded between two functions, we have to think a little more cleverly. So I tried to draw what that would look like revolved. What you really have is you have this sort of right circular cone, and then you have these sort of like humps that look like that in the middle of it. Anywhere you touch it, it dips in. You actually would have it, it would kind of come down to a piece, and it would smoothly cut in there, smoothly cut in at any given moment. So it kind of creates this extra funnel just there, and so you could create that. If you ever look at like interesting things in terms of like pottery and stuff that are made, not necessarily handmade but are manufactured made, they're usually described with this sort of cross section, and then it's just revolved around. If you've ever looked at something where the cross section looks exactly the same no matter how you cut it, it can be described like this, which is an interesting idea. So how do we do that? Well, what we want to do is when we don't have the tools to solve something, it's always helpful to go back to our original geometrical type of constructs. So we went back to the idea of the area of a circle and the area of a cylinder, or the volume of a cylinder, to develop this calculus-y way of summing up those areas to form a volume. And we're going to do the same thing, but instead of using just a disc, we're going to use this idea of a washer. So a washer is not a glazed donut. A washer is this idea of having a disc, and then you have a punched out hole in the middle. So I think in 2D it's actually called an annulus, maybe is the right term, but mathematicians always have really interesting words. But what we can do is we can say, okay, well, all right, if I have to cut out a piece, what I'm going to do is, and I'm going to go get a marker here. Let's get a green one here. Okay, so if I've got some sort of center, and I take a cross section, just that cross section there, what I see is I have some empty space. Oh wow, that sure is an angled line, isn't it? But assuming that was a straight line through, you have some sort of empty space from the center to that black strip, and then you have the shaded region that you're actually measuring. So what we're doing is the same idea over here. We have this point, we have an empty space, and then the shaded area we're measuring. So if I just revolved that piece around, what I would get is an empty space and then a space that's actually filled. Again, that's a cross section I've kind of angled this way. And so you'd have that filled in like this. So you get this idea of a washer. That's what you're doing. You're just revolving around, but you have some empty space. So what we can do here is we can say, okay, how do I represent what's empty and what's full? Well, if I'm representing the distance of the empty space, that's the distance from the x-axis to this sort of bottom function, sort of our inner function. So that's the distance to our inner function. And then I have some distance to our outer function, and that's our bounding here. So what I'm really doing is I'm really generating, in this case, I'm generating the volume of a right circular cone, and then I'm carving out. So let me get a few more markers here. So if I think about that, there's this whole volume here in that blue area. And what I'm really doing is I'm taking a right circular cone and then I'm cutting out that funnel. Cutting out that funnel from it. So the way to do that is to say, all right, I need the volume of the entire circular right circular cone, and then I need the volume of that entire blue region, and I'm going to take the volume of the big region, subtract the volume of the little region, and that gives me the final, that final green volume there. And I know I'm not explaining this perfectly, but you know, this is a tough concept. But what we do here is, all right, so if you remember, we go back to when we did the area between curves, we took that sort of outer function minus the inner function. We're going to do something similar for volume. We're going to take the outer volume and subtract the inner volume. And the way you did that with area was, this was actually two separate integrals and they just combined. So we can do the same idea here. We can combine them. We can pull the pi out front and we can say that that's the square piece minus the squared piece dx. Now, one thing I want to point out to you is very, very important. This is not it's not true. It is not the difference of the function values squared. It is the difference of the squared values of the functions. I know that's a little bit of semantics there. There's this huge difference. You can pick out any number of functions and this will not be equal to that. Not even close most of the time. So be very careful that you square the individual functions and do not square their difference. You take the difference once they're squared. Math terminology. Now you can also rewrite that. Since this is a difference of squares, you can actually rewrite this in the difference of squares factorization. This is sometimes helpful. It can be. It's not always helpful. But this can be helpful if there happens to be some interesting cancellation that happens when you either add or subtract them together. So use that at your discretion. I don't use this very often, but it is there. Anyway, again, the washer method, and this is the most commonly used method. The disk method is a stepping stone to this. The washer method, again, sets this whole idea up in motion. This is what you should be focused on, this piece right here. And we're going to do some examples to reinforce that.